here we're going to talk about recursive formulas. We're going to look at 3 different applications of recursion. The first will be just using functions. The second will be something called Pascal's triangle, and the third will be the Fibonacci sequence. So let's start by talking about let's start by looking at an example of a recursive formula. Now, a recursion just means that if you want to find something in the next step, you need to, in a sense, look back a step. So here, let's look at a function where f of 0 equals 3, and f of n equals, let's say, 2f of n minus 1 plus 3, let's say. Maybe I shouldn't put a 3. Let's do plus 1. There's a 3 up here, so who needs 3's all over the place? Let's put a 1 there. So f of 0 equals 3, f of n equals 2f of n minus 1 plus 1, and our goal here, let's say, find f of 3. Well, to find f of 3, all we have to start with are f of 0 and f of n. Now, f of 3 would be n equals 3 here, but notice to find f of 3, you would need f of 3 minus 1, which is f of 2. But we don't have f of 2. All we have is f of 0. So let's find f of 1 using this formula, then we can find f of 2, then we can find f of 3. So to find f of 3, let's find first f of 1. What's f of 1? Well, we use this formula down here. 2f of 1 minus 1 plus 1. Okay? That's 2f of 0 plus 1, because 1 minus 1 is 0, so we have 2f of 0 plus 1. f of 0 equals 3. So we have 2 times 3 plus 1. 2 times 3 is 6, plus 1 is 7. So here we have f of 1 is 7. Well, that's not what we want. We want f of 3. But we can now find f of 2. Because f of 2 is 2f of 2 minus 1 plus 1. Well, 2 minus 1 is 1. So we have 2 times f of 1 plus 1. Well, f of 1, it's not given over here, but we did just find f of 1 up here. f of 1 is 7. So we have 2 times 7 plus 1. 2 times 7 is 14 plus 1 is 15. Well, now we can finally find f of 3, because f of 3 is 2f of 3 minus 1 plus 1. Replace n with 3 here. 3 minus 1 is 2. So this equals 2f of 2 plus 1. f of 2 we found is 15, so this is 2 times 15 plus 1. 2 times 15 is 30. 30 plus 1 is 31. So we could define functions recursively. Now, you could have been asked here, find f of 100, and then you'd have to go through, what, 100 of those computations. I don't think I would do that to you. But another thing we can look at is a structure that's formed in a recursive manner. And the one we will look at is known as Pascal's triangle. Now, Pascal's triangle is an array of numbers. Well, it's an array of numbers that take a triangular shape. And to fill it in, you look at what happens in the previous row. So to start, we put a 1 at the top, and I'm going to put that a little lower. And then the next row, we're going to put 1s like this, and we're going to start them in a triangular manner. Now, the top row, I'm just going to label up here. Now, it's the first row. There are some times in math where it's convenient to start counting at 0, and there are times where it's convenient to start counting at 1. This is an example where it's convenient to start counting at 0. So that first thing we're going to call the 0th row. Then we're going to call the next thing the first row, and then the second row, and so on. Now, to form the second row, well, we'll start with a 1 on both sides. And all you do to fill in the rest of the numbers is look at the two numbers immediately before it. Notice the notice the 0th row has one number. The first row has two numbers. This next row is going to have three numbers. Start and end with a 1. Now to fill in this middle number, which goes here, we look at the two numbers above and to the right and to the left of it. So to the right, we have a 1. To the left, we have another 1. And to find this number, you add those together. So 1 plus 1 is 2. And that makes the second row. Now, the next row, the third row, well, again, we're going to start with a 1 on both sides. But in this row, we're going to need two more numbers. They go here and here. And to fill them in, you look at the two numbers immediately above this position, above and to the right, to the left of this position. So we're here. On this side we have a 1. On this side we have a 2. 1 plus 2 gives us 3. Over here, look up. On this side you have a 2. On this side you have a 1. 2 plus 1 is also 3. And we can keep going. Let's form the next row. I'm going to have to move my row designations over. This one will be 4th row, even though it's the 5th row. So we start with 1 and end with 1. We're going to need 3 numbers in here because we want there to be 1 number, 2 number, 3 number, 4 number, and here we want there to be 5 numbers. Start and end each one with a 1. Now here, you look in the two positions right above that, you get 1 plus 3, which is 4. Here, you look at the two positions above that, 3 plus 3 is 6. Here, you look at the two positions above it, 3 plus 1 is 4. And let's form one more row. Call it 5th row. Again, we're going to start and end with 1. Now we're going to need, I'm going to put that there. I guess I'll put this one on the next board. So we need 6 numbers here. Start and end with a 1. And here we get 1 plus 4, 5. Here we get 4 plus 6, 10. Here we get 6 plus 4, 10. Here we get 4 plus 1, 5. And so on. You can keep filling in rows. The next one might be a good exercise to fill in the next 2 rows. They would be 1, 6, 15, 20, 15, 6, 1, 1, 7, 35, 35. I missed a number. No, I didn't. 1, 7. Oh, I can't visualize. Oh, I did skip a number. 1, 7, 21, 35, 35, 21, 7, 1, and so on. But let's look at a couple properties of this. Now, this is a very useful triangle in many branches of math. It shows up in algebra, it shows up in combinatorics, fancy word for counting. We'll talk about a couple of its properties. First, you'll notice this diagonal here, 1, 2, 3, 4, 5, and then keep going, 6, 7, 8, and so on. Those are the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Let's look at the next row, or the next diagonal. I am going to fill in the next number for this. So we have 1, 2, 3, 4, 5, 6 there. Let's look at the next diagonal. Those numbers are a nice set of numbers geometrically. Anybody have any ideas why? I'm not sure if I would be able to answer that if someone just threw that question at me. I'll give you a hint. Bowling. That's how I see it, at least. That next diagonal forms the set of what is known as triangular numbers. Now, why are they called triangular numbers? Well, they are the numbers you can fill in a triangle using dots, equilateral triangle. So 1, I mean, that's kind of a null triangle. That's not a very important triangle. Well, it's not a very useful triangle, I should say. What about 3? Well, you can arrange 3 dots in an equilateral triangle like that. What about 6? Well, same thing. You can arrange them in a triangle like that. There are 6 dots arranged in an equilateral triangle, and so on. 10, you have 10 dots arranged in an equilateral triangle. 15, 15 dots, and so on. So you can see the next number would be 21. And I said that with bowling, those first 10 and bowling pins. I think that's the easiest way to see them, I guess. And you can keep going on with these diagonals, and they form other shapes of numbers. I'll just stop at the triangular numbers. You can read about the others on like a Wikipedia page. They're called the next ones are like I forget the word they use. It's like a 3-dimensional triangle type thing. Now, one other thing we'll do with these, we'll use these to expand binomials. What do I mean by that? Well, we're going to use this. We're going to see how we can use this. Sorry, my eraser is very squeaky today. We're going to use this to expand things that look like x plus y to the n. And this is one example where it's useful to start counting your rows at 0. So we're going to look at how we can expand this. And we've seen this all, like in a high school algebra class. You've definitely seen it with 2 and 3. You might have seen it with 4. I would doubt that. Usually they would stop at 2 or 3 because who wants to deal with 4? We will today, so I guess we want to. But as an example, x plus y to the first is just x plus y. Well, let's keep that in mind. X plus y squared. Well, what's x plus y squared? Well, you might remember from a high school algebra class that it's x squared plus 2xy plus y squared. But we can actually see all of that using this triangle. So let's expand this square using Pascal's triangle. Well, the way we will do that is by looking at the exponent. In this case, the exponent is 2. And that tells you which row to look at. Now, we're not looking at the second row down. We're looking, remember, we're starting at row 0. So 2 actually occurs in the third row down. The way I like to remember that is the row that has a 2 in the second position. And here, I'll circle the row, and we're going to use these numbers. Now, these numbers give us coefficients, 1, 2, and 1. So let's write them. So let's say x plus y squared equals 1, 2, and 1. Let's write the 1 and the 2 and the 1. And now these are all going to be added together, so I'm just going to write pluses before the 2 and the 1. I'm not going to write a plus before the first one because we don't need a plus at the beginning. That's assumed. Now, all we have to do with these coefficients set is now arrange these x's and y's. How are we going to arrange the x's and y's? Well, we want 2 letters on each piece, 2 total letters on each piece. The first one is an x. The second one is a y. You could work backwards. Let's not work backwards here. The first one is x. The second one is a y. Well, what we're going to do is start by putting 2 x's on the first thing. Well, we want 2 total letters. If we put 2 x's on the first thing, well, that would leave us with 0 y's on the first thing. Well, and now we started with 2 x's on the first thing. The next step, we're going to put 1 x on the next thing. We want 2 total letters. We put only 1 x. We also need 1 y. Remember, exponents are just a way of counting how many things you have multiplied together. So here, x squared is just 2 copies of x written next to each other. Or you could write it as x squared, which we will. And similarly, we have 0 y's, 1 x, and 1 y. Well, we started with 2 x's, and then we went to 1 x. In the last piece, we're going to put 0 x's. so x to the 0. We want 2 total letters. This number 2 up here tells us a lot about what we want. It tells us where to find the coefficients. It tells us the total number of letters we want on each of these pieces. 2x is 0y, 1x, 1y. 0x, if we want 2 total letters, then we need 2 y's. Well, that's written in a very complicated way. Let's get rid of all the 1's. Well, let's not write all the 1's, I should say. Y to the 0 is 1. X to the 0 is 1. So we have 1 times x squared times 1. Just x squared. Something the first, we don't write that 1. So plus 2xy. And over here, 1 times y squared is just y squared. So here we have expanded x plus y squared. Let's do another. Let's do exponent 5. Let's hope I have enough room. I'll have enough room. So expand x plus y to the 5 using Pascal's triangle. Well, x plus y, maybe I should write the 5 up here also. Well, x plus y to the 5, the exponent is 5. Let's look in the triangle for a 5 in the second position. So in that row, we have 5 in the second position. So this tells us all of our coefficients. 1 plus 5 plus 10, another 10, 5, and a 1. Maybe I'll write that last one a little closer. Now I'll leave it there, I guess. Maybe I'll move it closer as we go through this. So we set the coefficients. Now we just need to put the letters on. This is a 5, so we want 5 letters on each piece. Well, to start, we're going to put 5 x's there. Now, the way we did the one with the square, I just worked on this entire first piece, then the entire second piece. There's another way you can think through that. I actually like this second way a little more. 5 x's, well, in the next one, 4 x's. The next one, 3 x's. The next one, 2 x's. The next, 1 x. The last, 0 x's. So sorry I squeezed that. Maybe I'll just not squeeze it. I'm just going to rewrite this. I'll scribble that out. I'm just going to redo this so I'm not squeezing it there. X plus y to the 5th. We look at the 5th row. The row with a 5 in it, I should say. That gives us the coefficients of 1, plus 5, plus 10, plus 10, plus 5, plus 1. I think I'm squeezing again. God, I can't keep my space organized properly. 1, let's do plus 5 there. Let's move these plus 10s. Plus 10. There, this will be better. Plus 10. No, it won't. Yeah, it will, whatever. Plus 5, that'll be better. Plus 1. Okay. Yeah, that's still not optimal. That's just have to deal with that. So we put our coefficients. Now we need 5 of each letter, or 5 total letters on each of those numbers. So we'll start with x. That's the first variable there. We put 5 x's there. We put 4 x's there. We put 3 x's there. We put 2 x's there. We put 1 x there. And we put 0 x's there. And then we do the same thing with the y, but backwards. Notice we want 5 total letters here. So now we need 0 y's. We need 1 y, 2 y's, 3 y's, 4 y's, and 5 y's. So we started with x's, 5, 4, 3, 2, 1, 0. And then with the y's, we need 0, 1, 2, 3, 4, 5. And now we just simplify this, not writing all the 1's. We get x to the 5th plus 5, x to the 4, y, plus 10, x to the 3, y squared, plus 10, x to the 2, y to the 3, plus 5, x, y to the 4, plus y to the 5th. And you can check your work at the end also by looking at the coefficients and making sure these all add up to 5, and they go in the 5, 4, 3, 2, 1, 0, 0, 1, 2, 3, 4, 5 order. Now, there are many other applications with Pascal's triangle, in particular counting. We won't talk about any of those. And this, just as an example, this tells you what the number of sets of size, this number 3, for example, is the number of sets of size 2 in a set of size 3. So if you have a set of size 3, how many different subsets of size, well, maybe I'll just, I'm not going to ask any examples, this is just to illustrate another thing. So this is the row with 3, and that's the second entry in the row, that 3 that I circled. And one interpretation of that, one of many interpretations of that, is given a set of size 3, so A, B, C, how many subsets of size 2 are there? Well, there's A, B, there's B, C, and there's A, C. So there are three subsets of size 2 in the set of size 3. This gives you that actual number without having to write them all out. So if you had a set of size 5, so A, B, C, D, and E, 5 things in the set, and you wanted to know how many subsets of size 3 are there, well, this tells you there are 10. There are many things you can do with Pascal's triangle. I'm not going to ask anything like that. That's more for a combinatorics class. So it is definitely worth maybe even looking up Pascal's triangle and looking at some of the other applications of it. But I will restrict the questions I ask to the things we covered minus that last observation.